So we're going to talk a little bit about area and estimating with finite sums. And the reason we're going to talk about area is because we are beginning our exploration of integrals and integration. And what we're going to learn later is that an integral, a finite integral, really represents the area under the curve between these two bounds. But we're developing our process because we want to understand what an integral is. So if we look at this graph here, we have the graph of y equals 1 minus x squared. And so what we can do is we can determine exactly what that area of space is. And, leading towards some future logic, this could be represented in integral notation as saying the integral from 0 to 1 of 1 minus x squared dx. And so we've introduced these bounds here. These are finite bounds, and we're saying that this is as my x value moves from 0 to 1. Now, again, that's a little bit beyond where we are now. We're going to try and talk about how this integral definition is developed. So if we wanted to find the area under this curve, well, I don't know exactly what that shape is. That's not a geometric figure that I know a formula for the area of. However, I could approximate the area. And by approximate, I mean I could draw two rectangles. So you'll see here I've added another picture, and we have drawn two rectangles. So those pink rectangles have been drawn over my curve, the space R that we would like to find the area of. Now, these two rectangles, these are regular shapes. We know the formula for the area of a rectangle. It's length times width. So we have a width and a height, right? And I could find that area of the first one, and I could jump over to my second rectangle here. We have a width and a height, and I can find those two areas, and that would be close to the area of R. But as we can see, those rectangles, they cover more space. So this would be an overestimate for the area of R. And so if I say I made those rectangles with different endpoints, and maybe I had 4 of them, all of equal width, right? I'd end up with these 4 rectangles, and we'd be cutting out some of that area that we overshot there. So I've got a better picture of what we're looking at here. So here we've got 4 rectangles, and what we can say between these 4 rectangles, comparing it to the 2 rectangles, is that when we have the 4 rectangles, and I pulled the 2 back in here, is this extra space, this extra overestimate for our area is less space than when we had 2 rectangles, right? That's much more extra pink space, all right? So what we are supposing now is that the more rectangles, the better the estimate. And so my question is to you, how many rectangles could I create, right? The diagram here on the left shows 2 rectangles of a equal width, each 1/2 unit, versus 4 rectangles on the right, all of an equal width, 1/4 unit. So how many rectangles could I draw in this space between 0 and 1? And the answer is infinite rectangles. So we're building towards making more and more and more rectangles. And the more rectangles we create, possibly the less amount of error involved and the better approximation. Now, these 4 rectangles, this is the same picture we were just looking at, these 4 rectangles represent upper sums. or in this situation, a right-hand sum. So we're looking at the higher output or the higher y value on each of those quarter inch or quarter unit intervals. So how would this differ if I had chosen to draw my rectangles using the lower sum? So what you see here is I have drawn 4 rectangles using the lower output value or the lower height y value on any of these intervals. So what is the difference between the upper sums and the lower sums? Well, the lower sums underestimate. You can see that the area of these 4 shaded rectangles is less than the area of our blue curve R that we were originally looking at. And in fact, my 4th rectangle has a height of 0, so there's 0 area. So in this situation, the upper sums overestimate and the lower sums underestimate. And my question to you is there a way that I could choose these heights, which are coming from my output or my y value? Is there a way I could choose these heights that might be better? So I've added a third picture here on the right, and what we can see is that if I choose my height, right, my width is constant, my width for all of these rectangles is still just that quarter of a unit, but if I choose my height using the out point at the middle of each unit. So in this third picture, we are looking at the midpoint at the base of that quarter unit wide. So the midpoint is an eighth. So at 1/8, 3/8, 5/8, and 7/8, we can calculate these heights using the midpoint. So I'm calculating these y values. So I have a width and a height. And if you notice, looking at the picture here, we have a little bit of region where we have undershot and then a little bit of region where we have overshooted, right? Overshot. So we're missing some and we have some extra. And so what does that do if we have some missing, but hey, this some extra? You'll notice these triangles are similar, and it's not always going to be this nice looking, but they are similar in area region, so they cancel each other out. So in this situation, when we're looking at the midpoint sums, it is a better approximation because we have some extra and some under, and those regions that are missing or added, they cancel each other out. So I think looking at these 3 pictures, we should all be able to agree that the midpoint sum gives us the best approximation for the area. So going back to the question, how many rectangles can I create? In this situation, my width, my partition width, each of these is a quarter of a unit. But I can make that width for each of those rectangles smaller. How small? Infinitely small, right? So I'm going to bring in 2 more pictures. The graphic on the left here is a lower sum or right-hand approximation. And we can see there have now been 16 rectangles. And so we see that error for our lower sum, these little triangles that we've left off, the more rectangles we've added, that undershoot area is smaller. And the same here for my upper hand sum, my upper sums. on the left-hand side of each interval. We've got a little bit extra, but all of these little extra areas added up together are much smaller than, say, when we had 2 or 4 upper sums. So in both of these pictures that we're looking at here, we have 16 rectangles. And as I've mentioned, we can make the width of each of those rectangles infinitely small, so we have many, many, many more rectangles. And so if we look at our subintervals, the quantity of subintervals that we are creating. So we've looked at pictures now for 2, 4, and 16 subintervals. We started with the upper sum in our first picture. We said the upper sum overestimates it. So what you notice on that upper sum at 2 rectangles versus 4 rectangles versus 16 rectangles, that number is decreasing. And as we create more rectangles, say 50 or 100 or 1,000, what we notice is the sum, the area of that region we are approximating, is approaching a number which looks to me to be approximately 2/3. Now, the lower sum, which we said underestimates, right? So we start with a value lower, and you'll notice that as I create more rectangles, this sum, this area approximation is getting larger. And at 1,000 rectangles, once I've made 1,000 of those tiny little rectangles and added all their areas together, again, we get another value, which is decidedly close to 2/3. So let's look at the difference here for just the midpoint sum. So the upper sum is greater than that, and the lower sum is less than that. And the midpoint sum, pretty close to 2/3. 4 rectangles, the upper sum is above and the lower sum is below, but we're still close to that approximately 2/3 value. And so when you get down here to 1,000 rectangles, you start to notice, the more rectangles we are creating, the closer all 3 of these sums are to each other. The lower sum is still a little bit lower than our midpoint sum, and the upper sum is still a little bit greater than our midpoint sum. But all in all, it appears to me that they all seem to be approaching roughly 2/3. So it appears that this area is converging to a value near 2/3. So moving forward, we're going to look at doing some examples where we draw rectangles to estimate. And then the idea, building towards understanding what an integral is. An integral is when there are infinite rectangles. So we're going to start, we'll be building towards looking at a limit as the quantity of these rectangles, the number of subintervals, approaches infinity. So limits coming back into play, and then we'll talk about adding all these rectangles up. A little bit of summation notation will come into play.